રજા હોય કે ચાલુ હોય શું થયું આપે આવવાનો એટલે
Cancer. यस सर.
हाँ क्वेश्चन.
हाँ सर.
हमारा जो डिस्प्ले में है ना,
हाँ हाँ
स्लाइड वाला,
हाँ हाँ.
वो वाला रख दो आप.
ओके. श्योर श्योर
है ना?
श्योर श्योर.
बिल्कुल. जब वहाँ पे डिस्प्ले आए ना,
ओके ओके.
पहले वही दिखाने का,
श्योर.
अदरवाइज वीडियो दिखाने का. ठीक.
ओके सर.
ठीक है. जब कोई बोल रहा हो तो वीडियो दिखा देने का.
ओके ओके. ठीक ठीक. TV बंद करो बस. See that the button is super. हाँ सर।
आप अपने माइक है ना म्यूट कर दो, बहुत सारी आवाजें आ रही हैं यूट्यूब पे।
ओके सर, ओके ठीक।
an elixir of energy of India's independence, elixir of inspiration of the warriors of our freedom struggle, elixir of new ideas, pledges, and nectar of Atmanirbharta. This Mahotsav is dedicated to the people of India, and it is an embodiment of all that is progressive about India's socio-cultural, political, and economic identity. Through its planned activities, it aims at empowering youth, connecting people and state, and promoting deeper inclusiveness across the nation. Today is 28 February, and on this day, in year 1928, the great Indian physicist Sir C.V. Raman invented the Raman effect. We celebrate this day every year in India with a particular theme to show our respect to this famous Indian scientist for his extraordinary contribution in the field of science. Today's event is planned under the umbrella of Azadi Ka Amrit Mahotsav with the theme Integrated Approach in Science and Technology for Sustainable Future. The main objective behind today's celebration is to spread a message about the importance of science in our daily lives and also to display the glimpses of activities, efforts, and achievements in the field of science for human welfare. To celebrate National Science Day, today's event is organized jointly with Indian Society of Remote Sensing, Ahmedabad Chapter, Indian Society of Geomatics, Ahmedabad Chapter, Indian Meteorological Society, Ahmedabad Chapter, Space Application Center, SAC, Ahmedabad, and Development and Educational Communication Unit, DECU, Ahmedabad, in outreach coordination with Gujarat Council on Science and Technology, GUJCOST, Gandhinagar. Let's start today's program with a formal welcome address. May I now request Dr. Parul Patel, ma'am, Chairperson, Standing Committee, Azadi Ka Amrit Mahotsav at SAC, to welcome the gathering joined with us today through virtual mode. Please, ma'am.
Thank you, Chair. Respected Professor Abhijit Sen, the world-renowned theoretical physicist. Respected Sri Nilesh Desai, sir, Director SAC and President ISRS. Respected Rajesh Jyoti, sir, Associate Director SAC and Chairman of Indian Society of Remote Sensing, Ahmedabad Chapter. Shri Rajesh Khandelwal, Director DECU. Dr. Narottam Sahu, Member Secretary of Gujarat Council on Science and Technology. Dr. Rajkumar, who is Chairman of IMSA Ahmedabad Chapter. Dr. Karthikeyan, Chairman of ISG Ahmedabad Chapter. Dr. J.K. Pandit and ISRO HQ team who has joined with us today. Colleagues of ISRO centers, all the faculty members, students from across the country, and all the participants. A very warm welcome to this Azadi Ka Amrit Mahotsav that we are celebrating as National Science Day, that we are celebrating as part of Azadi Ka Amrit Mahotsav. We know that entire nation is celebrating Azadi Ka Amrit Mahotsav. And as part of Azadi Ka Amrit Mahotsav celebrations at ISRO, we have conducted a number of activities like showcasing the frontiers, space frontiers, what are the achievements that we have as country. Like a lot of planetary missions, the science behind it, the technology behind that, the kind of sensors technology that goes in. We have had like what kind of launch vehicles we have, the Indian space history, past, future, current and future, which direction we are going. We have also tried to understand through various space exhibitions and taking this space research to small villages through our static and space on wheel exhibitions. And in addition to like very important events like Khadi exhibition, Rashtriya Ekta Divas, and many more of this kind. This National Science Day, you know, this time the theme of National Science Day, as she has mentioned, that we celebrate as discovery of Raman effect by Dr. C.V. Raman. And the theme is Integrated Approach in Science and Technology for Sustainable Future. See, for all of us who are in the space field, we know how important it is to understand that how do you, what are the effects of this space debris and how do you manage those space debris. So in that context, today's topic that we have is by Professor Abhijit Sen. He's going to discuss on the remote sensing of space debris using plasma effects. So that way we are going to have a very deep understanding, like his deep insight will be benefited through this talk. So I'm very much sure that all the participants will take benefit of this, and many people have joined through YouTube and our SAC's. In fact, we have kept it on internet website of SAC, so for benefit of all our professional bodies and all the other participants. So this event we could not have organized, but for the guidance and encouragement by Director SAC, Director Deku, Rajiv sir, Chairman of ISRS AC, Chairman of ISGAC and IMSA. And Dr. Narottam Sahu has always been supporting us through this outreach and taking it to for the benefit of all the students and faculty across the country. So we are my heartfelt thanks to all of you, sir. And I once again welcome you for this event that we are really looking forward to.
Thank you, ma'am. As we all know, we celebrate National Science Day to encourage people to make significant contribution in scientific arena for human welfare by popularizing science and technology. With this vision, under the banner of Azadi Ka Amrit Mahotsav, we organize today's event, National Science Day, which has taken its form under the guidance and exceptional leadership of distinguished scientist Shri Rajiv Jyoti sir, Chairman, Indian Society of Remote Sensing, Ahmedabad Chapter. Sir is also an Associate Director at Space Application Center. May I now request Shri Rajiv Jyoti sir for giving us brief insights about the importance of today's event. Please, sir.
Yeah, good afternoon to all. Let me at the outset welcome Dr. Abhijit Sin, our eminent speaker of today's program. Director of Space Application Center, as well as the president of the our ISRS national body. So, on behalf of our local chapter, ISRS Ahmedabad chapter, I welcome you all today for this event. This ISRS is a platform where we always have such programs where we share the knowledge among the researchers, among the scientists and our professional experts from industry, academia and different organizations. So today is also one of the efforts towards that. And incidentally, I want to say that this week is very important because we had launched our RISAT-1A satellite, which was going to do remote sensing of the ground of our Earth, wherein going to have a lot of information for our agriculture, for our land, our water bodies and all, forest and so many things, for many applications which are useful for our society. And we never thought that today we are also going to have a issue with the debris in the space. Initially, time when we started this journey of space, we had we always trying to launch as many as satellite, and today maybe others, for the information of others, we also have ISRO, and particularly I was also involved into that we have developed a multi-object tracking radar, which is again based on the concept of a phase array system, where we are able to track the debris from ground itself. So the relevance of this topic is very apt today because we are having a lot of issues with the space. A lot of debris are being there. Many techniques are being evolved to ensure that we don't face any casualty once we launch the satellite in light of those small satellites which are being launched in the low orbits. So, sir, we are eagerly looking for your talk, and I'm very sure it will enlighten our people to understand how we can use the plasma effect for micro remote sensing of space debris. So once again, I thank you, our eminent speaker and all the participants to make it very successful, this program. Thank you, sir.
Thank you, sir. Continuing with the scientific fervor and celebration further ahead, under the banner of Azadi Ka Amrit Mahotsav, Director SAC Shri Nilesham Desai sir has always been our guiding force, our mentor and our pillar of strength. Sir has made various remarkable contributions in ISRO's space missions and has successfully led the design and development of ISRO's airborne and spaceborne microwave remote sensing payloads. Sir has guided activities for the development and realization of advanced and synergistic applications involving Earth observation, SATCOM, and SATNAV applications for societal benefits and strategic uses. May I now request Shri Nilesham Desai, sir, Director, Space Applications Center, for his inaugural address. Please, sir.
Thank you, Richa. And at the outset, let me thank Dr. Abhijit Sen, Emeritus Professor and INSA Honorary Scientist at IPR, Gandhinagar. Sir, thank you for accepting our invitation and agreeing for this talk. So let me thank and welcome you for this National Science Day. And also let me greet the participants as well as the scientific community on the eve of this National Science Day 2022. And as Parul Madam said, it is the integrated approach of science and technology for sustainable future. That is the theme of this year's National Science Day. And all of us know that we are celebrating it in commemoration of Raman effect. This got in 1928, and in 1930 he got the Nobel Prize for that. And country is in fact now due for another Nobel Prize. I hope so. At least by 2030 we have another Nobel Prize in this field particularly. Of course, many people of Indian origin have got the Nobel Prize in science and technology after that, but it is a different feeling if somebody from India working within India gets the Nobel Prize. So let us hope that this feeds into further developments related to science and technology. And the topic of today's talk, and that too by such an eminent speaker, such a learned scientist, that is remote sensing of space debris using plasma effect. So, and we have in ISRO, we have set up an Office of Situational Awareness where we support all these activities related to eliminating space debris and the studies associated with that. And as Rajiv has rightly mentioned, MOTR and other tracking radars we have been developing and installing at various places in this country for observing space debris and trying to see how we can mitigate. So debris mitigation is going to be one of the important topics in future. And all of you may be aware that he mentioned about our recent launch of RISAT-1A. But in fact, RISAT-1, which was our first radar satellite, which was launched in 2012, after 4.5 years, suddenly one day it stopped working. And when we tried to locate it and try to find out the reasons, afterwards NORAD informed us that it has split into two parts. And they could locate two elements in the space. Of course, afterwards, again, after 15 days, it started working. So that theory may not have been correct. That is what we afterwards concluded. But this is the impact. And that too, that time they said that something has impacted our radar spacecraft. And that has created this issue of getting it mechanically split into two elements or two parts. So that shows the relevance and importance of space debris and how it is going to affect our future space activities. So that's why this topic is very relevant as far as space debris and its mitigation effects, and how using plasma effect we do remote sensing, and then maybe it may help us to mitigate also. So we would like to hear with interest the talk of Dr. Abhijit Sen. And as I said, he is a very learned man, well experienced, and with lot of scientific publications and work behind him. So it will be real pleasure to listen to sir. And as I said, space debris, different techniques are being used. And recently, all of you would have heard about that Starlink 40 satellites getting damaged due to the geomagnetic storm. So that also has resulted into debris, and with the plethora of satellites, especially for space for internet, that is generally going to be the theme in future. And many countries, many institutions and organizations are coming up with their different constellation of low Earth orbiting satellites. So that will increase this danger of space debris in near future, and that is going to affect the other legitimate space activities of agencies like ISRO, NASA, European Space Agency and all. So space debris is a very critical issue, critical subject, and it is going to be, and this problem is going to increase only in near future. And that's why to learn about that, to work on that for various studying first through remote sensing and then trying to mitigate his effect is going to be an important area of study as well as research, and then finally doing some technical implementation to overcome this problem. So once again, I compliment ISRS Ahmedabad chapter as well as all the associated societies, Indian Society of Geomatics, Indian Meteorological Society, and Space Applications Center, DECU, and other teams who have joined together to arrange this very important talk today on the eve of National Science Day. So once again, I thank Dr. Abhijit Sen sir, as well as welcome him for this talk at Space Applications Center. We would have loved him to greet him and welcome him in person, but better during some next time and on a other relevant occasion. We would like to invite sir and have discussion with him on various relevant topics. Thank you.
Thank you so much, sir. Moving ahead, may I now request Dr. Mehul Pandya, sir, Joint Secretary, ISRS Ahmedabad Chapter, as well as Head of Division at SAC, to give us a brief introduction of our today's honorable guest speaker.
Thank you, Richa. It's my honor to introduce today's distinguished speaker, Professor Abhijit Sen. Professor Abhijit Sen is a theoretical physicist who did his undergraduate studies at St. Xavier's College, Ahmedabad, and obtained his PhD from University of Tennessee, USA. After his postdoctoral work at Oak Ridge National Laboratory, USA, he joined the then fledgling plasma group of the Physical Research Laboratory, Ahmedabad, and subsequently helped establish the Institute for Plasma Research, that is IPR, at Gandhinagar. So he is one of the founding members of the IPR. Professor Sen served as a Dean of IPR for several years and later held the S. Chandrasekhar Chair Professorship. He is currently an Emeritus Professor and INSA Honorary Scientist at IPR. He has held visiting scientist positions at various international centers, including the Research Laboratory of Electronics at MIT, USA, and the University Aix-Marseille, France. His primary research interests are in basic plasma physics with applications to controlled magnetic fusion energy, nonlinear phenomena in laboratory and space plasmas, intense laser plasma interactions, and also in dynamical studies of ensembles of coupled oscillators to model collective behavior in biological and neuronal systems. He has played a leading role in founding and development of National Magnetic Fusion Program in India and has served and as an expert member in many international scientific bodies, including one of the most important ones, the International Tokamak Experimental Reactor ITER project. Professor Sen is fellow of many prestigious academies. He is fellow of the Indian Academy of Sciences, the Indian National Science Academy, the National Academy of Sciences India, and the American Physical Society. He has also served as president of the Gujarat Science Academy during 2008 to 14 and chair of the Plasma Physics Commission during 2003 to 5 of the International Union of Physics and Applied Physics. We are privileged to have Professor Sen for delivering this invited talk today on the occasion of National Science Day. When I talked to Professor Sen over phone for his invited lecture, he readily agreed for it. So we thank you for that. And Professor Sen is a very good orator who can describe a complex physical phenomena in a quite simpler manner. And he has all our distinguished earlier speakers said he has selected an appropriate topic on this event, which is very apt for the occasion and very, very important for the remote sensing community. So I invite Professor Abhijit Sen for delivering the lecture. Over to you, Professor Sen, please.
Can I share my screen now?
Yes, sir.
You'll have to permit me for that.
Yeah. Already given, sir.
Okay, thank you. It's asking for some permission.
Sir, you are presenter.
Yeah,
You share your screen. It will do, I think.
yeah, but for sharing, it is asking for some permission. I don't know why.
Uh-huh.
Yeah, I got it.
Sir, are you able to see that share screen tab?
I think you'll have to give me that permission again. It's not
Yeah.
sharing it.
Sir, you are one of the organizers now. I think it should be
It says I'm still not the presenter.
okay. फिर से करिए आप. हाँ तो लॉग आउट हो गया एक बार.
Yes, sir. Now you try.
Okay.
Sir, it is showing. Yeah, it is showing you are presented. Yeah, great. Your desktop is visible.
Visible now? Yeah.
Kindly make full screen.
Okay.
Okay, sir. Great.
Okay, good.
Good to go, sir. Yeah.
Okay. Well, thank you very much, first of all, Dr. Pandya, and also all the distinguished audience that we have today, particularly Honorable Sri Nilesh Desai, Director, Dr. Jyoti, and also thank all the sponsoring societies, particularly the Indian Society for Remote Sensing, ISG, IMSA, Technology-GUJCOST. It's a great honor to be here today. A particular thanks to SAC. As an old member of PRL, I spent almost half my career there. And being there in the early days, when I saw actually SAC growing within PRL, I have a real feeling of kinship with people of SAC. So whenever I'm invited to give a talk in SAC, I feel very happy and honored. So it feels very nice to be here today, even though it's a virtual meeting. but coming to SAC audience always means like visiting your extended family. So thank you again for giving me this opportunity. About the topic today, it might seem a bit presumptuous on my part to talk about remote sensing to people who are world experts in remote sensing here. Also to talk about space debris, again, people who are dealing with it on a daily basis, and you know the ins and outs of this subject. My knowledge basically is in plasma physics. That's where I work on. Hello? Yeah. So, So I hope the experts here in this field will excuse me if this talk seems very elementary to them. Because it's a popular talk, I've made it quite elementary. But I think there's a new element in it. And one of the motivations for my talk, and the reason why I readily agreed to Dr. Pandya's request, is that we have a new idea, which I would like to bounce off you, who are the experts in this field, and get your expert advice and technical know-how, so that this idea can be pushed forward and developed into a practical tool for detecting debris. If that happens, then my talk will have been worth it, and it will also succeed in fulfilling the theme of today's Science Day, namely an integrated approach to science and technology for the future of society or for societal benefit. So let me start at the very beginning and talk about and give some perspective and background to this problem. Okay, start moving ahead. Okay, did you get the next slide? Yeah. Is that visible, the next slide?
Yes, sir. It is visible, the growth of space traffic.
Okay. So let me start with this slide showing just the growth of space traffic since the early days. So when I was preparing this slide, I had a bit of nostalgia about this whole thing. Because if you remember, the whole space age started with the launch of Sputnik in 1957. I was a schoolboy then. Tells you how old I am. I was then in the 9th grade, I believe. And after Sputnik was launched and it was traversing the sky, one of the teachers of our school in St. Xavier's High School, Loyola Hall, had actually spotted it from the terrace of the school at night. At that time, the nights were really very pristine. One could see many of these things. So he got very excited and he called up the press and told them. So next day, this was the news item in Times of India. And it created quite a stir in the usual very sedate air of Ahmedabad in those days. And our school kids were very excited, and we actually went up to the terrace with him the next day in the evening and saw this little speck of light move across the sky. That was the beginning of the space age. And as you can see, in the 1960s, these are spots of spacecraft or space objects in the sky. You see very few of them, because soon after the US launched, and then a few others. By 1970s, this population has started to grow quite a bit. I think 75 we joined, and the first Indian satellite went up. By the 1990s, you can see that this has become a very, very crowded affair here. And as you go on to 2010, things are getting really crowded. So these are only pictures of objects that are greater than 10 centimeters, as viewed by various diagnostics both from the space as well as from the Earth. So there's a very nice review of this by Eric Christensen, a report from NASA Johnson Space Center. So just to give you an idea of what this involves, here is a graph that I've plotted here, which shows the monthly number of objects in the Earth orbit by the object type. So you can see the total objects are something like 17,000 here. This is in 2013. Okay. But out of that, only 1,100 are operational spacecraft. The rest of it is all debris. So there's all mission-related debris because there are rocket parts, satellites which
This
are not working
conference
anymore.
will now be recorded.
And also all the debris that you generate while launching any satellite. So this is the kind of affair which was happening in 2013. And as you can see from the curves themselves, that there is no sign of slowing down. In fact, space activity has grown to a phenomenal amount, and therefore this problem is going to keep on multiplying. It's actually reaching the threshold of what's known as the Kessler syndrome, which means that now if you have a lot of debris, then the chances of colliding with this debris increases with the amount of debris that you have. Of course, some of these things are getting lost because they come down and then get absorbed. But you will reach a point when if this density of debris reaches beyond a certain critical point, then you'll have more and more collisions and you'll generate more and more debris. So there'll be an absolutely exponential rise, and that will be disastrous for all space assets. So that's what we are heading towards. So what is the remedy? This was 2013. If you want to see what is the picture today, you can go to this site, which actually gives you a day-by-day, hour-by-hour picture of what the situation looks like in the low Earth orbit region. So according to the US Space Surveillance Network, there are about 500,000 objects in the sky there, which are about greater than 1 centimeter. So the network tracks about 20,000 of these, and these are only those that are greater than 10 centimeters. These include debris as well as the operating satellites. But the estimate is that there are more than 100 trillion smaller pieces that cannot be tracked. So some of these, of course, are very, very small. They are almost like sand particles. So they have no immediate danger, but over time, they are like a sandpaper that will rub against the satellite bodies and, really sand it down. So that's one danger. But objects in the range of 1 to 10 centimeters, these are the most dangerous and pose a great threat to active space assets. And these are also the objects that cannot be tracked optically, and they are also very difficult to be tracked by radar. So what is the damage potential of these small debris objects? So you should remember that in this LEO region, where they're about 400 kilometers above the Earth and beyond that, these objects have very high velocities or hypervelocities, something like 7 to 8 kilometers per second, which means about 25,000 kilometers per hour. So they are really whizzing past very fast. So even a small object of a few grams has enormous kinetic energy and can cause significant damage to a spacecraft. So this is a simple rule of thumb that if you have a small, let's say, aluminum sphere moving at 7 kilometers per second, it can completely pierce an aluminum shield, which is 4 times the thickness of the sphere's diameter. So this is a great danger to any body of a satellite, for example. It can go straight through. Here is a picture I have shown that if you have a 1.3 centimeter diameter sphere moving at 7 kilometers per second, this is the kind of rupture that it can cause. Here is the size of the debris, and this is the kind of hole it can make in the body. So it's very important to find means of tracking these small debris objects. So how do you do this? How do you locate these invisible debris? So I think that's where plasma will come in. So basically, one looks for their footprints. If you all remember this novel about the Invisible Man, you might have even seen the movie for that. How do you track the Invisible Man? When he's finally walking on the sea sand, you see the footprints. And that's how you know that he is walking there. This was a very favorite method of Sherlock Holmes. And this is one of the quotes from this Hound of the Baskervilles. And they say they were the footprints of a gigantic hound. And that's how they tracked what was causing those deaths in this particular novel. So how do you look for their footprints? Well, the main clue, and this is the physics idea that I would like to get across, that the debris objects are not neutral objects. Because they are floating around in the ionosphere, which means they are surrounded by plasma, they will get electrically charged. Because as they move along, electrons and ions continuously keep bombarding them. So these get absorbed on their surface. And after a while, they develop a surface potential. So they are negatively charged. All depends on where they are at what height they are. If they are at very high, if it's only solar radiation causing the loss of electrons from them, then they'll get positively charged. But the fact is, wherever they are, they will get charged. And therefore, they have to be treated as being charged objects. Now, being charged, since they are moving in the plasma, they will also perturb the plasma, as any charged object would do. And therefore, they'll create fluctuations in the ionosphere, or all kinds of collective waves. So what kind of waves? In many ways, the plasma is like a fluid. Of course, it's a charged fluid, but a fluid nevertheless. In most approximations, you can think of it like water or any other liquid. So the clue is, one can look what happens in an ordinary fluid, in liquid, for example. Let's say in water. So you know what happens in water if a body is moving in the water. If you take the example of a simple boat moving in water, it creates these waves behind it. These are called wakes. The same thing also happens in a plasma. If you take a very strong charged particle and make it move in a plasma, you leave a trail behind it, and these are called wakes. This is a picture taken from an actual plasma experiment where they actually used a plasma which was visible, something called a dusty plasma. I'll come to that later. But as you can see, the analogy fits quite well. There's the same kind of phenomena happening behind the charged particle. But something funnier happens even in a liquid. For example, what happens when the boat moves very, very fast? It is faster than the phase speed of the surface wave that it is creating. So this is something that's not too well known, but it has been investigated a lot in fluid mechanics for some time. So the idea is the following. What happens is that the boat can not only create a wake behind it, but it can also excite some waves ahead of it. And these waves are called precursors because they are going ahead of the boat. And these precursors travel much faster than the boat. So if you see a boat traveling at a very high speed, and it creates these precursors, and if you're on the shore, you will see the precursors coming at you. From that, you will know that the boat is following, it's coming behind these precursors. These precursors take the form of something called a soliton, and I'll explain that in a minute. So here's a cartoon picture of what this phenomena is. Supposing you have a channel of water, shallow channel of water, and you have an object below on the floor of this channel. And let's say you pull it with a velocity u. Now, if this velocity u is larger than the speed of the surface wave that you create, then not only do you have these wakes behind, but you also excite these lumps of waves ahead of it. And these travel very fast, faster than the speed of u. This thing is, of course, invariant. You can go and instead of moving the object, you can move the liquid over it. So for example, if the liquid were moving in this direction, again, you would have the same kind of waves. So the liquid is moving in this direction, which means in the frame of the liquid, the body is moving in this direction. And therefore, again, you will have the same phenomenon. Okay. So this is Galilean invariant, as they say. So this is the phenomena. Now, what are these solitons? This has actually been experimentally observed in ships moving in canals when the ship's speed is much greater than a certain critical speed. Actually, this became quite a problem in England, particularly when these very fast ferries were invented. So these ferries were moving so fast that they created all these very large waves. In fact, they created giant waves. So there was a particular incident called the Harwich Incident, where a 5-meter wave was created. And actually, when it hit the shore, there were some small boats moving around there, people fishing and all that, and it killed actually 2 people. So after that, they put up this sign that what should be the speed of the ferry? It should not exceed certain region. If it exceeds this, then this is where you create solitary waves or solitons. So before I move on, let me say a word about solitons. What do we mean by soliton? So a soliton is nothing but a localized pulse-shaped wave structure. You can think of a little mound of water. And they travel at a constant speed, but while they're traveling, they maintain their shape and size. And they really live a long time. This is unusual because normally if you create a little pulse in the water, after a while it will just spread out, or it's called, it disperses. But these are very special waves. They're called nonlinear waves. As you know, if you increase the amplitude of a wave, it starts steepening. When you are in the sea, on the beach, for example, in the ocean, you see these ocean waves coming in. And as they come in, their amplitude grows and they become steeper and steeper, and finally they break. So that's an effect which is exactly opposite of what happens when a perturbation disperses away. But you could reach a state where there's a balance between the nonlinear steepening and the dispersive effect. And then you create a stable structure which can last forever. This is something that was observed many, many years ago. It was in 1834 by a Scottish engineer. His name was Scott Russell. And so he was in charge of inspecting some of this boat traffic in canals. So one day when he was riding on a horse, he saw this boat being pulled by 2 ropes along there. And suddenly the rope snapped. So the boat abruptly stopped. And in front of it, it pushed the water so much that it created a mound, and this thing traveled very fast like a soliton. So he followed it on horseback for quite a few miles and saw that it had not died down. That was the first observation, and later people developed a theory for it. Mathematically, the solitons are very special nonlinear solutions. There's a whole branch of mathematics that has developed in the solution of nonlinear partial differential equations. But physically, you could imagine that these solitons almost behave like particles. In fact, if 2 of them collide, they go through each other and they are not destroyed. It's exactly like a particle. Solitons are common in many systems. They occur in light pulses in fiber optics, neuronal pulses, plasma waves. For example, when we send an impulse from our brain to our hand or to our finger, it takes the form of a soliton. The advantage is that when it passes through a junction, there are other nerve pulses that are going through. Now, if they were not solitons, they would destroy each other. Your finger would not know what message your brain has sent. But because they have this special property that they retain their identity, you are able to feel what your brain is, despite so many other pulses passing through these nerve centers. So that's a special property of a soliton. Okay, here's a little picture showing what happens when 2 solitons collide. You can see that they are going through each other without destroying themselves. This is a picture of Scott Russell, and recently in 1995, they recreated the whole experiment and created a soliton, and people watched it. And now, solitons have also been observed using radar scattering. This is a picture of atmospheric waves creating ocean waves. So here you have a synthetic aperture radar observation of the sea surface, where you see imprints of upstream atmospheric solitons. So here's an island, and you can see the island here again. So the wind is blowing in this direction. So in the frame of the wind, you can imagine the island is moving in that direction. And you are creating waves in the upstream direction. And these were observed to last for a very long time. So this is a direct proof of this kind of atmospheric solitons being created, or ocean wave solitons being created. And this is taken from a picture using a radar from a satellite. So what is the physics of this precursor solitons? Why does it happen? So basically, when an object is moving through the water, it's pushing up the water in front of it. If the speed of the object is slow, or slower than a critical velocity, slower than the velocity of the phase speed of the waves, then this density pileup will soon disperse because they all travel with their phase velocity and just go out. And that's what forms the wakes that you know behind the wave. But if the wave is moving very, very fast, then this is not possible because those things cannot move away that fast. So the thing keeps on building up. And once it builds up, that means the amplitude is increasing, nonlinear effects take effect, and therefore you might reach a point where this nonlinearity balances the dispersion and becomes a soliton. Once it becomes a soliton, its speed is faster than the object, so it will separate from the object and move away. So that is the physical origin of what happens in a fluid when you create these solitons.
Professor Sen, we can see your slide, but we can't hear you,
see?
sir.
Oh, okay.
Yeah, we can see. Yeah.
Okay.
Yeah, we can see.
Okay. So basically, the idea that we got was from this observation in fluids, that you can create a precursor soliton for an object moving in a fluid. So the thing was, can you do the same thing in a plasma? If supposing you have a charged particle, consider it as a debris, which is a charged object. If it moves in a plasma, can it create, for example, precursor solitons ahead of it? Because then you can detect these precursors and you would have be able to detect the object. Now, surprisingly, when I looked at the literature and researched all over, nobody had done this thing in a plasma. The fluid literature was separate, but nobody had attempted to create precursor solitons in a plasma. So we thought, in principle, we should have a similar physics applying. For example, when the velocity of the object is greater than, let's say, the corresponding sound velocity in the plasma, with something called the ion acoustic speed, then you should have ion acoustic solitons created. So because nobody had explored it in plasma physics, we thought we would try it out. So we had already developed the theory for it that seemed to predict that. But the basic test has to be done in the laboratory. So we set up a simple experiment in IPR to test this idea. And I'll just tell you how we did it. We did it in a dusty plasma. Why did we do it in dusty plasma? Because a dusty plasma is nothing but a plasma in which you sprinkle some dust. By dust, I mean objects that are, finite size, something that you can see with your eyes. Whereas, a plasma consists of electrons and ions, and there's something you don't see at all. They're very tiny. So compared to that, these are huge objects. So if you shine a laser light on them, then you can actually see these objects moving around, and therefore you can detect what's happening. So here's a little tutorial about what a dusty plasma is. If you inject this object in a plasma, then these solid particles absorb electrons, ions, and they get charged. Exactly what's happening to the debris in the ionosphere. And you can also have secondary emissions. So finally, they'll get charged and they get the normal. So this behaves like a third component of the plasma. You have an electron fluid, an ion fluid, and a fluid consisting of dust particles. Okay. So what can you do with this? The advantage of a dusty plasma is that actually you can see the dust moving. You can also see the waves moving. Here's an example of what happens when you have dust acoustic waves. You can see the wave fronts. This is taking a video, and then you analyze the video pictures. You can see that, what the wavelength is and what the speed is. All this can be. Similarly, you can see how it is moving here, that how it's moving up and down. So you can get the frequency, you can get the speed, whatever you want to do. You should all do this offline and without disturbing the plasma at all. So that is why we chose a dusty plasma experiment to do our experiment here. So this is a simple device. It's very easy to create a plasma like that. This is basically a glow discharge tube where you have two electrodes, an anode and a cathode. When you strike a discharge, you have a gas like argon, you create an argon plasma. And then inside that, you sprinkle some dust. There's some dust lying on this cathode. And because they get charged, and because there's an electric field associated with each of these electrodes, it's like a sheath, these things get levitated. So gravity pulls them down, electric field pulls them up, so they settle at some level. So you create a dust cloud, which you can then observe, and you can create different waves in it. So this is the experiment we did. This is a picture of the device, if you want to see. Really a tabletop device. This is what the plasma looks like. And then when you put in dust, you can actually visualize this dust, and you'll see in a second. So what was the idea? Now, how do you make this dust cloud or make a charged object move in this? So rather than moving the charged object, we thought we will move the dust fluid itself. You know, remember that fluid experiment of in the canal, where you can either move the object or you can move the fluid over the object. So the object here was a potential hill. Remember, this is a charged fluid, so you need a charge potential. So potential hill was basically we had a grounded wire. It creates a sheath around it. There's another electrode here, and therefore there's a sheath around that. Between these two sheaths, you confine the dust cloud. Then you suddenly change the potential of this hill. So from grounded wire, it can become a floating wire. So then, of course, like a water flowing over a dam, all this dust cloud will flow over this and move in this direction. And you can control how fast this will move by controlling the height of the potential hill and how fast you're bringing it down. That was the simple idea. And this was done by one of the students and my colleague, Pintu Bandyopadhyay, who really did a great job of getting a very clean experiment to prove this. So what were the results? So when the dust flow, the dust is flowing in this direction. Here is the wire over which you can imagine a potential hill. So when the dust flow was in, and it was subcritical. So for example, the velocity was, the sound velocity is 2.4, but the velocity of the flow was 1.8. So it is below the sound speed. Then you only got waves. Now, because the dust is flowing in this direction, you imagine the wire is moving in the opposite direction. And therefore, you see waves behind it. So imagine this as the boat moving from left to right, and the waves are behind it. Then, when we made the speed higher, we made it to exceed the sound speed, something very dramatic happened. So now you still have these waves behind, but now you can see ahead of the wire. Imagine again the wire is moving in this direction. You have these waves which have strong structures, which are equally spaced, and they're moving at a very fast speed. So these are the solitons. This is a intensity profile of these solitons. So we actually measured and checked to see whether they were solitons or not. I won't bore you with the mathematics of this. But basically what we found is that these were traveling faster than dust flow and the dust acoustic speed. They were emitted at periodic intervals, and they maintained their amplitude after saturation. So they're the same features as what one has for a soliton. We even carried out tests. One of the properties of the soliton is the product of the amplitude and their width square is always a constant. So that's what we found for all these structures. We even modeled them using a famous mathematical equation called the KdV equation, where you add a forcing term because you are moving the liquid. And we found that exactly whatever happened in the experiment is reproduced here. This is the wire position, and you can see these solitons being emitted at the front. So we carried this thing forward. We even, instead of just using a simple KdV model, we took the whole fluid system and simulated them. And this, you can see, this is the source moving in this direction. Time is in this axis here, and you can see these soliton structures being generated one after another. Here's an animation of this thing. Here's the source moving, and you can see these solitons being created in the front. Then we went one step deeper. We even carried out molecular dynamic simulations. So since we said that, it's a fluid, maybe plasma is not quite a fluid at the particle level. So we did interaction of point particles and looked at the same thing. Again, we found that when the velocity of a charged particle is higher than a certain velocity, you had all these solitons being created ahead of. So this is for a single particle. To compare with the experiment, we took several of them so that it looks exactly like what is there in the experiment. It's like a line charge moving. Again, you can see very nice solitons being formed. So there was no doubt in our mind that theoretically and also the basic experiment, you could create solitons by moving a charged object through it. And this is the even further thing when we did it even more in-depth study, did a particle in cell simulation. So here you have a disk which is moving, which is closer to the realistic situation of a debris particle. And you can see how these, one after another, these solitons are created. So this is the irregularity crowd that you would like to detect. So these are fluctuations in either electric field or magnetic field. And these are something that you can measure from the ground or from a satellite. So that is the idea. So then we did some numerical estimates. Can you, for example, detect these signals? So for the LEO region, for example, if you just took plain electrostatic waves, see the orbital velocity is about 8 kilometers per second. And for the given plasma conditions there, sound velocity is 1 kilometer per second. So this is certainly moving much faster than this. So you can estimate what the electrical charge on a 1 centimeter object is and what is the surface potential. Remember, this surface charging is something that all of you are familiar with, at least in Isro. That's what happens to the satellites. They get a surface charge, which actually you would like to avoid because sometimes they can have sparks, they can damage things like your solar panel and all that. But this is something happening naturally to the debris as well. And the kind of surface potential that develop depends on the temperature of the plasma around it. So for example, here, the temperature is this much, you get about 0.7 volts. So there's some shielding around that. So finally, the potential is around 5 millivolts at a distance of 5 dB length. So the soliton width is about a few centimeters. So can you detect this? So this is actually this size and the amplitude. These are within the range of equatorial spreader. This is what ionospheric physicists are regularly measuring. So they are either measuring it with in situ probes or radar backscatter, digisonde, etc. So this is well within the technological limit of measuring from ground-based experiments. In fact, you can make this even better. We talked only about these simple electrostatic excitations. If you now excite electromagnetic solitons, like magnetosonic waves, or these are other collective modes of the system, because remember, there's also a magnetic field in the ionosphere. So the plasma is magnetized, and therefore you can have Alvin waves, you can have combination of Alvin and sound waves called magnetosonic waves. These have much larger footprints, something like 100 centimeters, a meter or something, and in some cases even few kilometers. So these would be easy to measure. So that's the basic idea. So what's the next step? So before I go on to the next step, let me again recap the basic idea and what are the premises. The key point is that you have to recognize that the debris object is a charged object and it is moving in a charged medium, namely a plasma. And therefore, it will create imprints in the plasma in the form of wakes and precursor solitons. Now, this concept we have already established by a variety of ways, done theoretical modeling, we have done computer simulations, both fluid, molecular dynamic, and particle in the cell. And we have also done laboratory experiments, which show that this is in principle happening. And we also, from the estimates, we also find that such precursors should be detectable by radar scattering, and therefore they can aid in tracking small debris objects. Now, this is where the next step comes, and which is what our distinguished director as well as Dr. Jyoti have emphasized, that now you have to convert it into technology. And that is where your expertise lies. So how do we do this? I'm suggesting here two ways, but I'm sure there are many other ways that you have. One way is, can we initially look for precursor solitons around a larger debris, not just 1 centimeter, because any debris will generate these things. So that you can simultaneously track by optical means this debris object. And therefore also, and if you see the debris object as well as if you by radar, you track the solitons, and you can associate the two of them or establish a correlation between them, then you will have proved the technical feasibility of this method. Other thing is that these excitations or these solitons or precursors are already there. They're already being, the only thing to do is to try and associate them with a particular object. So this is a question of measuring correlations between debris orbit and the existence and location of these solitons. So this is like this is a challenging task, but basically you have to, it involves huge amount of data analysis, examining all the satellite data that we have in this field, and then trying to, you can now use all these modern AI and machine learning techniques to find these correlations. So that's another way of doing it. So let me end by giving a proposal for a possible Isro R&D initiative. In fact, that's what I'm interested in. I'd be very happy to talk to people to see if we can develop this idea any further. Because as we know, ISRO has both the technological wherewithal and the scientific as well as technical expertise to develop this physics-based concept further into a useful tool for meeting the debris challenge. While doing this, there are rich possibilities of testing the physics on a larger scale. See, we have done it on a very small scale in a tabletop experiment. But you can do it on large space simulation chambers, which you have in many of your centers. And also you can make use of in situ measurements from the array of scientific satellites that you have, including CubeSats and the one that you've recently launched. The above effort can be expanded and enhanced by involving university groups involved in space research. Then one has to carry out an engineering feasibility study based on the available sensing and tracking facilities. Since our paper came out in 2015, there's of course been a lot of theoretical development by other people. Other papers have been written, but there's also been preliminary initiatives, international initiatives in this direction by NASA, AORD, and other agencies, where they are exploring this concept further. But I feel strongly that we should be doing it here, and that we can really make a jump start. And that is one of the main motivations of my talk to you today. So basically, I wanted to bounce this idea off you, and I would like your expert comments, technical feedback, and criticism of this concept, and suggestions about how to take this forward. If that happens, then I think this talk would have been worth it. Let me end by acknowledging all my co-workers in this, collaborators who have helped me develop all these things. Some of them have been my past students, others have been fellow colleagues at IPR. So with that, I think I would like to end my talk here. Thank you very much.
Thank you, Abhijit, sir. We are really honored to have you, sir, with us today. Your presence and enlightening words has helped in inspiring all the people to enhance their scientific zeal who have joined with us today from the academia and our viewers from across the nation through virtual mode. Thank you once again, sir. We now invite our viewers and participants, more preferably be called science enthusiasts, to please put forth your scientific queries. Your questions will be coordinated by our expert with a very vast knowledge, Dr. C.P. Singh, sir, Secretary, ISG, Ahmedabad chapter, as well as senior scientist at SAC, and your questions, viewers, will be answered by our esteemed guest speaker, Professor Abhijit Sen, sir. CP Singh, sir. Please, sir.
Yeah, thank you, Richa. We welcome our participants to write their questions in YouTube chat box, if possible. And since there is no question in our chat box right now in the GoToMeeting platform as well, I request if some of you are having and wish to ask directly, you can unmute yourself and ask. Otherwise, we are going to ask few questions from the
CP,
from here itself. Okay, Dr. Mehul Pandya is here with us, and he would like to ask few questions to Abhijit Sen, sir.
Yeah. Yes, sir. First, a comment. Thank you very much for very excellent lecture, and we are so glad to hear about you are continuing this research in one of the frontier fields of space debris, along with many of your research topics. Sir, I have small query as far as detection of these solitons are concerned. One of the slides which attracted my attention, and I thought it is very important, where you show in LEO orbits, where you describe about some of orbital velocities and charge and surface potential and those calculations. So what I thought, some debye length which you showed 0.3 centimeters, which is very important factor in coming out with the solitons width of few centimeters. That is what I remember in your slide. How does, sir, debye length of 0.3 centimeters is worked out?
So this is basically from the temperature of the plasma around it. It's actually 3 centimeters. And what the density there is. So that's how you work it out. So that's the shielding that the plasma does of any charge.
Okay, that is that sheath of plasma layer.
So what happens to the soliton width is a few debye lengths, and that's why you estimate the width of the soliton to be that.
Okay, sir. And the another question, just for understanding, if we are very happy, at least you have been touching upon this one of the gap areas through this particular method of exploring or at least detecting some of the space debris. Once theory is proposed, some clues are there, some modeling has been done, some practical demonstration is also done. By some of observations from ground, how that total surrounded area or total around or orbital paths around the Earth, how one can judge about total debris? Is it should be on some sampling based, or how do we can't cover the entire space around Earth for judging total number of
No, that's true. See, right now some tracking is already being done, as I said, by many agencies, including, I'm sure, Isro. You are tracking many of these objects, particularly those that are likely to collide with your specific spacecraft. But this tracking is right now limited to objects that are greater than 10 centimeters, let's say, or even larger. Okay. The problem is that objects which are much smaller than that, let's say a centimeter or 2 centimeters. Although they are small, as I showed, their potential for damaging a spacecraft is enormous. And those are very difficult to track. So therefore, if you can track those, that will be a big benefit for debris tracking. So that is the idea, that it will work for even these small objects. For the big objects, you don't have to worry, because those you can track optically. And then you can give an instruction to the satellite to move from that.
Many of them are catalogued also. So
yes, they're all catalogued. But those that are not, so this is to extend and expand your tracking ability. That is the idea.
Okay, thank you, sir.
Now we have one question. Actually, it's not a question, it's just an observation by Dr. Satyendra Bhandari on YouTube channel chat box. I would just read out his observation, sir, and we'll look for your comment. He says that there may be good possibility to observe the described signatures moving ahead of large debris by looking at GPS signals, depending on the scale and magnitude of the effects. So what do you feel, sir? Whether GPS signals can also be utilized to observe these solitons?
That's a possibility. Yes, so that is why I'm seeking suggestions and criticism from all the experts here in ISRO who are doing this night and day and in various wavelengths and various frequencies. So what are the possibilities of tracking these things?
Yes, sir. And definitely, we all would love to see you, sir, here physically, and we would have a discussion on this particular topic among the various experts that we have here. Sir, another question from Himanshu Patel is that what is the maximum orbit altitude of debris which can be detected by this method?
Oh, well, that depends upon where you are detecting it from. If it's ground-based, it depends upon your radar signal and its strength and how much you can. But if you do in situ measurements using satellites in that, so for example, if you want to make measurements in the geostationary orbit, where again there's a significant amount of debris, not as much as in LEO, then some in situ measurements can be done from satellites, and that should be possible.
Okay, sir. So now we are coming to the end of it, the question answer session. Now, Dr. Rajak wants to have some queries from you. Over to you, sir.
First of all, thank you so much, Professor Sen, for such an illustrious lecture. I have just a small query. It is with respect to the object, moving in our Earth's ionosphere. And,
yes.
We may detect them as you suggested. And obviously, once we detect, then we have to take some protective measure. So can you just tell me how much time we will have in such case that we can take any, protective measure?
Okay, so these waves, solitons, as I said, they travel very fast. For example, the ionoacoustic speed, as I said, was 1 kilometer per second. So that may not be enough because, maybe it will be enhanced by a factor of 2 or so. But if you look at magnetosonic solitons or solitons which are electromagnetic in nature, their speed is much higher because they are like the Alvin wave. And that can be much, much faster. And you can have probably more than a few seconds or maybe a minute or so before you can take some action. So I don't know whether that is enough to alert a satellite or not. How long does it take to alert a satellite? But by using a variety of means, you can certainly get some time to do this. And the other thing is that once you have tracked them, then you also know their orbits. Even if they're not on the colliding path, you can predict how their orbit is decaying or when will they actually come into the path of a given satellite. So that is the whole point of right now mapping all these debris. So this might help you do that even in a better way.
Thank you so much, sir. Thank you. And I think with this, we come to end of this question answer session. Over to you, Richard.
Thank you, sirs. As per our culture, we always felicitate our chief guest, but due to COVID-19 pandemic situation, we are doing it virtually today.
Thank you. Thank you very much. It's a real pleasure. Yeah.
Thank you once again, sir.
Okay, thank you very much.
The kind of response and the words of appreciation that we received from our viewers today is very overwhelming and it means a lot. We believe that our today's lecture by Honorable Guest Speaker, Professor Sen sir, will prove useful to our listeners. We plan to come up with such scientific talks and lectures in future as well. A great team equals a splendid event and a flawless execution of an event plan. To show our gratitude to each and everyone who has contributed either directly or indirectly towards successful realization of today's event. May I now request Dr. Dhaniram Rajak sir, Secretary, ISRS Ahmedabad Chapter, and also the alternate chairperson Standing Committee Azadi Ka Amrit Mahotsav at SAC to deliver the formal vote of thanks. Please, sir.
Thank you, Richa. A very good evening to one and all. It's a real my honor to propose this vote of thanks on behalf of Indian Society of Remote Sensing Ahmedabad Chapter, Indian Society of Geomatics Ahmedabad Chapter, Space Applications Center Ahmedabad, Development and Educational Communication Unit Ahmedabad, Indian Meteorological Society Ahmedabad Chapter, and Gujarat Council on Science and Technology Gandhinagar. First of all, we express our gratitude and thanks to today's speaker, Professor Abhijit Sen, who is Emeritus Professor IPR Gandhinagar, for accepting our invitation to deliver this online lecture. Thank you so much, sir. The topic of your lecture was so apt. It was very interesting and related to space debris issues, then plasma technology and our sustainable future. I'm sure everyone who has viewed it and who participated in this lecture, they have enjoyed it thoroughly. The question answer session was really very interactive and fruitful. Thank you so much, Professor Sen. On behalf of all the participants and on my own behalf, I thank Director Nilesh Desai, Director Space Application Center, Sri Nilesh Desai ji, for always encouraging and guiding us and delivering today's inaugural address. As we know, today's activity was led by ISRS Ahmedabad Chapter, which is chaired by Sri Raju Jyoti. Our heartiest thanks to Raju sir. We also thank Dr. Rajkumar, Director NRSC, Chair IMSA, Sri Rajiv Khandelwal, Director DECU, Dr. B. Karthikeyan, who is Chair of ISGAC, Dr. Parul Patel, who is Chair Azadi Ka Amrit Mahotsav SAC, and Dr. Narottam Sahu, who is Advisor at GUJCOST, for their support in organizing this event. Sir, we could not have approached you without the full support and cooperation of Dr. Mehul Pandya, who is Joint Secretary ISRS. Thank you so much, Dr. Pandya, for all your efforts and support. I also heartily thank Dr. C.P. Singh, who is Secretary ISG Ahmedabad Chapter, and Dr. Abhishek Chakrabarti, who is Secretary IMSA. Then Dr. Dhurbi Bharwad, who is Secretary Azadi Ka Amrit Mahotsav Ahmedabad. Then Richa Srivastav, who is Member ACAM at SEC, for providing their full support in carrying out this activity. I have been supported by my friends and so many people from here in SAC, DECU, and CISF. I really acknowledge their support and express thanks to each and every one of them. We organizers are extremely thankful to all the members of ISRS-AC, SAC, DECU, IMSA, ISGAC, GUJCOST, Isro headquarter, various universities, institutes, organizations, students, and all the viewers who have joined YouTube, who have joined through GoToMeeting, who have joined through SAC website Biome, for their participation. And because of their participation, this program has really become a good success. Thank you, everyone. Now, may I request all the participants who have joined through GoToMeeting link to kindly switch on their cameras so we can have some screenshot. So kindly switch on your video. We would like to have some screenshots. Yes, some more, please. So I think now screenshot is over. So Richa, now over to you.
Thank you so much, sir. Thank you so much, everyone, for joining with us today. With this, I, Richa, signing off.
Thank you, sir. Thank you all.